Normal Distributions Part 2. Area under normal curve using table. Example 1. Using the standard normal distribution, find the probability that a randomly selected standardized value from a normally distributed variable is less than negative 1.51. This can also be described as finding the area under the normal curve that is below 1.51 standard deviations to the left of the mean. A cumulative standard normal distribution table gives us the probabilities associated with z-scores. We are looking for the probability associated with the z-score of negative 1.51. So we will try to find the entry in the table where the row is negative 1.5, intercepts with the column 0.01. We find this value to be 0.0655. The graph at the bottom of the table shows that these 4 decimal place values in the body of the table correspond to the area under the curve that extends from the left tail up to the z-score itself. So, this value of 0.0655 would correspond to the area under the curve that extends from the left tail up to the z-value of negative 1.51. In probability notation, we would write the probability that z is less than negative 1.51 is equal to 0.0655. Area under normal curve using table example 2. Using the standard normal distribution, find the probability that a randomly selected standardized value from a normally distributed variable is greater than 2.33. This can also be described as finding the area under the normal curve above 2.33 standard deviations to the right of the mean. As seen before, the cumulative standard normal distribution table gives us probabilities associated with the z-scores. We are looking for the probability associated with the score of 2.33. So we will find the entry in the table where the row 2.3 intersects with the column 0.03. We find this value to be 0.9901. The graph at the bottom of the table shows that these 4 decimal place values in the body of the table correspond to the area under the curve that extends from the left tail up to the z-value. So this value, 0.9901, would correspond to the area under the curve that extends from the left tail to the z-value 2.33. But our requested probability calls for the area that extends from the z-value 2.33 up through to the right tail. But since the total area under the curve is 1, the area under the curve to the right where the z-score is 2.33 would be 1 minus 0.9901. That would leave 0.0099 as the area under the curve to the right of the z-score equaling to 2.33. In probability notation, we would write the probability that z is greater than 2.33 is equal to 1 minus 0.9901, which is equal to 0.0099. Area under normal curve using table example 3. Using the standard normal distribution, find the probability that a randomly selected standardized value from a normally distributed variable is between 0 and 0.95. This can also be described as finding the area under the normal curve between the mean and 0.95 standard deviations to the right of the mean. The cumulative standard normal distribution table gives us probabilities associated with z-scores as we've seen before. We are looking for the probability associated with the z-score of 0.95. So we'll find this entry in the table where the row 0.9 intersects with the column of 0.05. We find this value to be 0.8289. The graph at the bottom of the table shows that these 4 decimal place values in the body of the table correspond to the area under the curve that extends from the left tail up to the z-score. So, this value, 0.8289, would correspond to the area under the curve that extends from the left tail to the z-score of 0.95. But our requested probability calls for the area that extends from the mean, or in other words, where the z-score is 0, up to the point where the z-score is 0.95. But since the normal distribution is symmetric about the mean, the area under the normal curve from the left tail up to the mean, where the z-score is 0, is 0.5, or in other words, half of the distribution. That would leave us with 0.3289 as the area under the curve from the mean, where the z-score is equal to 0, up to that point where the z-score is 0.95. So the area that we're looking for is 0.3289. In probability notation, we would write the probability that z is between 0 and 0.95 is equal to 0.8289 minus 0.5, which is equal to 0.3289. Area under normal curve using table example 4. Using the normal distribution table, find the probability that a randomly selected standardized value from a normally distributed variable is between negative 2.07 and 1.88. This can also be described as finding the area under the normal curve between 2.07 standard deviations to the left of the mean and 1.88 standard deviations to the right of the mean. The cumulative normal distribution table gives us the probabilities associated with the z-values as we've seen before. We are looking for the probability associated with the z-score of negative 2.07. So we will find the entry in the table for the row negative 2.0 that intersects with the column 0.07. We find this value to be 0.0192. We will also look for the associated value with the score of 1.88. So we'll find the entry where the row is labeled 1.8 intersecting with the column 0.08. That value is 0.9699. The graph at the bottom of the table shows that these 4 decimal place values in the body of the table correspond to the area under the curve that extends from the left tail up to the z-score. So the value of 0.0192 would correspond to the area under the curve that extends from the left tail to the z-score negative 2.07. The value 0.9699 would correspond to the area under the curve that extends from the left tail to the z-score 1.88. But our requested probability calls for the area that extends from the z-score negative 2.07 up to the z-score 1.88. So the area that we are looking for is the difference between these values, which is 0.9507. In probability notation, we would write the probability that z is between negative 2.07 and 1.88 is equal to 0.9699 minus 0.0192, which is equal to 0.9507. Let's go ahead and follow along in our student notes. Let's take a look at the definition of the standard normal distribution. The standard normal distribution is a normal distribution with a mean of 0 and standard deviation of 1. Note here that the mean is 0 in the middle, and to the right is +1 standard deviation, and to the left is -1 standard deviation. The formula for the standard normal distribution is as follows. Again, it's a bit complicated, and we don't use it that often. However, it is useful at times. All normally distributed variables can be transformed into the standard normally distributed variable by using the formula for the standard score. The following is a very, very important formula, where you take the value minus the mean and divide it by the standard deviation. Again, it would be wise for the student to take note of this very important formula. Once you calculate the z-score, you can then go ahead and take the z-score and notice that it is the number of standard deviations that counts. In particular, it's the number of standard deviations that a particular x value is from the mean. Table E in Appendix A gives the area to 4 decimal places under the standard normal curve for z values from -3.49 to +3.49. Technology can also be used to find the area under the standard normal distribution curve. Finding areas under standard normal distribution curve. Step 1. It is always best to draw the normal distribution curve, then shade the area under consideration. Step 2. Choose the appropriate type of problem and either use Table E in Appendix A or use technology to find the shaded area. Let's take a look at some examples. Here, we're going to go ahead and look for the area that's under the standard normal distribution curve to the left of the z-value. Let me emphasize the word left. This is probably the easiest example of all. When you are looking for the area to the left of the z-score, you simply use the area that's given in the table itself. I'll explain why in a moment. First and foremost, it is best to sketch the curve here. Once again, a normal bell-shaped curve would indicate normal distribution, where 0 is in the middle, which means 1.32 will be somewhere around here. And since we are looking for the area to the left of 1.32, we shade from this point to the left all the way off into negative infinity. Once again, we are looking for the area of this shaded region. Now, as you recall, the total area under a normal distribution curve is 1. And as you can see here, a vast majority of this area has been shaded in. The next step would be to look at the table. Here is a table where we have our negative z-scores. Since we have a positive z-score 1.32, we need the other side to the table, which display the positive z-scores. In this particular case, we are looking for the z-score of 1.32. In order to look for the z-score of 1.32 in this table, you first start by looking at the row that contains 1.3. Then you combine that with the column that contains the decimal 0.02. Building these two numbers up gives you, in fact, the number 1.32. Then you zoom in to where they are intersecting each other, and you'll notice we get 0.9066. So taking a look once again at our area to the left of 1.32, according to the table, the probability is 0.9066. Now, what about finding the area to the right of a specific z-score? Here, you do something similar where you go ahead and find the z-value in the table itself, as I showed from the previous example. Then you subtract the area given from 1. So a slightly different approach. Once again, let's go ahead and draw our graph. Here we have a normal bell curve. 0 is in the middle, which means negative 0.67 will be somewhere around here. So to find the area to the right of this z-score would require us to subtract its value on the table from 1. The area to the left of negative 0.67 is actually 0.2514. So subtracting that area under the curve from 1 will give us the shaded region above of 0.7486. Again, this is how you find the area to the right of the z-score. What if we wanted to find the area between two z-values? Here, you simply find the z-scores and the corresponding z-values on table E, then subtract their corresponding areas. So drawing this normal curve will look as follows. Now again, z equaling 0 will be smack dab in the middle. 1.45 should be somewhere around here, and 2.32 will be somewhere around here. So we are looking for the area between these two scores. Again, go to the table and look for the number 1.45 and look for its corresponding value. Do the same with 2.32. Look for its corresponding value. I invite you here to pause the video, look at the table again yourself, and verify that in fact we're going to be subtracting the values of 0.9265 and 0.9898. Now it's best to subtract 0.9898 minus 0.9265 to get a positive area, since area should always be positive. The answer in this case is 0.0633. Let's go ahead and do a few more examples. Here, let's find the area between two given z values. In this case, we'll look for the area between z equals 0 and z equals negative 0.32. So please go ahead, take a look at the scores on the table. The table clearly indicates that z equals 0 is smack dab in the middle of the bell curve, which means to the left of 0 will give us 50% of the area. A quick drawing would prove this. We all know that the mean is 0, which is right in the middle of the bell curve. And the area to the left of smack dab in the middle of the bell curve will give us an area of 0.5. The value we find at negative 0.32 will give us 0.3745. So I invite you to pause the video here and confirm this with the table. You can find this table in the back of your text or in the e-text under the area that says End Matter. If you need help looking for the table, please contact me and I'll be more than happy to show you. How about let's look for the area that's to the right of 1.23. Now remember, when you're looking for areas to the right, that means you need to subtract from 1 the value found at this particular z-score. Well, at this particular z-score, we get 0.8907. And notice I'm subtracting it from 1, because once again, we are looking for the area to the right of that number. That will give us the answer of 0.1093. And again, a quick sketch of the graph will help you make sense of this. 0 in the middle, 1.23 will be around here somewhere, and the area to the right would be here. So once again, you subtract it from 1. And notice it's a relatively small area, leading us to a relatively small probability. Now, for anything that says to the left, you simply just use the table value that's found in Table E. So if you go ahead and pause the video here and search for the number negative 1.03, you should find the table value of 0.1515. Once again, please pause the video here and confirm this yourself. Knowing where these values are coming from in the table will certainly help you moving forward. This is a concept that's going to follow us for the rest of the semester, and you certainly don't want to miss out on this. And finally, let's look at the area between negative 2.15 and positive 0.97. Once again, here we will be taking the larger area and subtracting it from the smaller area. Notice here in the normal curve graph, it looks as follows. Z equals 0 in the middle. Negative 2.15 will be somewhere over here. Positive 0.97 will be somewhere over here. And we're looking for this entire area from these two z-scores. As you can see, it's a quite large area of the bell curve, so we should get quite a large probability. Again, locate these z-scores on the table and verify. The area to the left of 0.97 should correspond with 0.8340. And the area to the left of negative 2.15 should correspond with the area 0.0158. Subtracting these values, again, as I mentioned before, will give us a rather large probability of 0.8182. Now here, we're going to go ahead and find the probabilities for regions between two z-values. In this example, we'll be doing the same exact thing using the table to find these probabilities. It's just using different notation. So for example, let's look for the probability of z being between 0 and 0.92. Now again, the graph will look as follows. Z is in the middle of 0, and somewhere to the right of 0 is 0.92. So we're going to be looking for the area between 0 and 0.92. Now keep in mind that 0.92 is pretty close to 1. And if you recall, area to the right of 0 by 1 standard deviation will be half of 68%. So the answer here should be right around 34%. So let's go ahead and find out if that's true. The solution here is 0.8212, which corresponds to the number 0.92 on the table. And obviously, 0.5, which is right in the middle, corresponds with a 0 z-score. And as I mentioned earlier, this answer should be somewhere right around 34%, or 0.34. And notice our answer happens to be 0.3212, which makes sense. Here, we are looking for the probability that z is less than 2.77. This is probably one of the more simpler examples, because here, z less than means you're looking for the area to the left of 2.77. So here, we go ahead and look at the score of 2.77 in the table, and the corresponding value located there will give us the area that we need. In this case, 0.9972. 2.77 is pretty close to 3, and we all know that 3 standard deviations to the right or the left of the mean will give us quite a bit of the area under the bell curve. Next, let's look for the probability that z is greater than 1.12. Here, this means we're looking for the area that is to the right of 1.12. So once again, we need to be subtracting whatever value we find in the table from 1. The table that corresponds to the z-score of 1.12 in the table, again, pause the video and verify, will be 0.8686. So again, 1.12 corresponds to the value of 0.8686 in the table. Subtracting this from 1 because we're looking for the area to the right of 1.12 gives us 0.1314. Now let's go ahead and do one more where we're looking for the area between two z-scores. Once again, we're going to be taking the larger area and subtracting the smaller area. Pause the video here. Look for the values that correspond with negative 1.20 and 1.56. Then confirm your result with mine. Here, 1.56 corresponds with the value 0.9406, and negative 1.20 corresponds with the value of 0.1151. Subtracting these values, we get an answer of 0.8255. Finally, let's find the two z-values, one positive and one negative, that are equidistant from the mean, so that the area in the two tails totals 5%, 2%, and 1%. Let's start with the first part, where the area in the two tails totals 5%. So how would that look like in a sketch? Keep in mind that the middle is 0, and we're looking for a z-score to the right and a z-score that's to the left that are equidistant from the mean. Shading to the right of z and to the left of z should total for us 5%. Now, since the two z-values have 95% between them, thus 5% in the tails, what that means is that each tail will contain 2.5% of the area. Clearly, 2.5 plus 2.5 gives us our 5%. So simply, all we need to do is go to the table and look for the z-value where you have a correspondence of 0.0250 in the table itself. You'll notice that that corresponds to the z-score of negative 1.96. And all we simply have to do now, since they are equidistant from the mean of 0, the other number will simply be positive 1.96. So once again, negative 1.96 and positive 1.96 will be our z-scores in question. For 2% in the tails, you'll notice the tails get smaller here. Where I have my negative z-value here, and equidistant to that will be my positive z-value here. So again, we are looking for the areas in those two tails adding up to 2%, which tells us that the area of each tail will be 1%. Again, 1% plus 1% will give us our 2%. So in this case, The two z-values have 98% between them, and thus 2% in the tails, meaning once again that each tail contains 1% or 0.01. So here we go ahead and search for the closest value on the table that is the closest value to 0.01. As you can see in the table, that value happens to be 0.0099, which corresponds to our negative z-score of negative 2.33. Therefore, our positive z-score will be positive 2.33. And finally, for 1% of the tails, we go ahead and sketch as follows. Now here, 1% will give us in the tails very small tails for the negative z and positive z values. Notice here we have very little area to work with here on both sides. In fact, the area of each tail will simply be 0.5%. Now you'll find a problem here because the areas listed on the table do not range this small. So here you'll notice that even though each tail contains 0.5%, we need to look at the z-value with an area of 0.0050 to the left. However, you will not see such a value. Instead, you need to look for the halfway point between negative 2.57 and negative 2.58. But in this case, we go ahead and choose the value with the greater absolute value for more accuracy. Therefore, our negative z-value will be negative 2.58, which makes our positive z-score positive 2.58.